In this lab, we will test out the microcontroller's capability to run at low energy, meaning a couple of microamps instead of several milliamps, and using the real-time clock to accomplish this goal. So last time we worked with a regular timer or clock, whatever you call it, timer counter. And there's this limitation for almost all microcontrollers that the timers, which are timer peripherals, they take their clock source from the same source that is used by the CPU. So as mentioned before, you can use some prescaler, but the clock is derived from the CPU. So if prescaler is 1, then the clock is running at the same speed as the CPU. It's 14 megahertz. And running a processor at 14 megahertz consumes a lot of power. And it consumes a lot of electricity. However, to make a microcontroller be able to run from a couple of microamps, there is a second level of clocks, which is called low energy clocks or real-time clocks. Let's check out in the datasheet. So in my development kit, under documentation, I select reference manual for this CPU, and there is this clock management system, clock management unit. As you can see here, there are several oscillators. In this picture, it's a little bit zoomed out, but generally there are two main domains of clocks, which are high frequency clocks, 14 megahertz or 48 megahertz, and they are all channeled to the CPU and to high power peripherals like timers, I2C, Cortex, DMI, and so on. And the second domain is the low energy, low frequency oscillators, low frequency RC oscillator and low frequency external oscillator, and they can all be channeled to low frequency peripherals like low energy sense, real-time counter, low energy timer 0. There's one dedicated timer that can be run at low frequency during CPU sleep. And basically what we can do is we can set up low frequency, low power real-time clock to be clocked from low frequency RCO, consuming something like 0.9 microamps, very small current. And then we can switch off the high frequency clock, and this will make the CPU go to sleep. And after some time, the real-time counter can wake up the CPU. It switches on back on the high frequency oscillators and does its magic, does the work. And when it's done, it can go to sleep, and the real-time clock will wake it up after some time. So let's try to program this with a very simple example. So basically what we want to do is, for example, we want to set up our microcontroller in such a way that, for example, it wakes up every 1 second and, for example, blinks the LED. It sleeps, then it wakes up, turns on the LED, goes to sleep, sleeps, wakes up after some time, again after 1 second, turns off the LED, and so on. So, just a simple example of real-time counter, sleep modes, and energy consumption. And this way, we will also see the energy consumption there. So to do that, we will make a library called system time, and we will just write some code for time management. So in our project, on source folder, you right-click, choose new header file, and let's call it systime.h. Finish, and right-click on the source folder, new source file, systime.c. So in systime.c, first line is hashtag include, double quotes, systime.h. And in systime.h, we will include some libraries that we want to use. So obviously, if we want to use real-time clock, then we need to include its mlib library. So under mlib, right-click on Browse Files here, and then real-time clock RTC. So these EFM32 microcontrollers have two types of real-time clocks, real-time clock and real-time clock plus calendar. I think that this processor only has real-time clock, not real-time clock and calendar, as you can see, RTC. And in this list, it has backup real-time counter and real-time clock somewhere. Oh yeah, real-time counter here and backup real-time counter. So basically the backup real-time counter and real-time counter differ by the following thing. Backup real-time counter can have a separate pin that you can connect to a separate small coin cell battery. And even if the CPU is off, this battery feeds this clock so that it remembers the time between microcontroller restarts. When a microcontroller, switches on, it can read the actual time because this thing has a separate power supply pin. I don't know if it doesn't have a schematic picture, but generally this backup real-time counter has a separate pin through which you can feed it. We will use the real-time counter probably in this example because it's a bit more common. Or let's check out, maybe we can use the backup real-time counter. So let's try to do that. The backup real-time counter is a 32-bit counter and it's clocked either by 32.768 kilohertz crystal oscillator, RC oscillator, or 2 kilohertz RC oscillator. But generally, it's 32 bits. And prescaler is up to 2 to the power of 7 is 128. So 32, 7, 6, 8 divided by 2 to the power of 7 is 128. So 256 ticks per second. On the other hand, real-time counter is 24 bits, but it can be divided by up to 2 ticks per second. So 32, 1 second. So it's 32, 32,768 divided by 2 to the power of 15 is 16, approximately 16,000, don't remember the precise value, but it will give you 2 ticks per second. So we will use this. What we need to do is drag and drop the EM real-time clock library into our mlib folder, choose link to files, studio SDK location, okay, and in our system, we immediately write hashtag include double quotes em rtc.h. And let's write a small, simple example program where we initialize real-time counter to make an interrupt every 1 second and toggle LED number 1. So either on or off. And we will do it through interrupts. So in this systime.h, we will create a function which we will call void init systime init. It's a good practice to start a function with the library name and then underscore and then what this thing does. Then if you have many libraries, you immediately understand from which library the function comes and how it would work. So systime init void systime h, here we will create it. you need to press save all, and then you can start using the real-time clock library. So we can go to real-time clock documentation in mlib, Rtc, and just like everything else for this processor, we can use this real-time counter initialization type def structure, which we fill up with our settings, and then we feed it into real-time counter init, and then it starts to work. However, by default, if we look at the clock management unit, the real-time counter can only be clocked by low-frequency oscillators, which are by default off. Everything, when you start up the CPU in ARM architecture, usually everything is switched off, every one of these oscillators, except high-frequency RCO, which is directly connected to the CPU so that the CPU can start working. So if we want to use real-time clock in low-energy mode, we need to turn on low-frequency real-time RCO, low-frequency RCO. It is an internal built-in moderate precision oscillator. So to do that, we will need to do the following thing. Also, we will need to hashtag include em clock management unit.h. It's already dropped and dragged and dropped here. So low frequency peripherals are clocked for the settings through high frequency core clock, high frequency low energy clock source. So basically the peripheral is running from low frequency RCO, but to configure them, we also need to turn on high frequency low energy clock so that this bottom part is actually switched on in general. And then we attach them to low frequency. So the first line that we need to write is clock management unit underscore clock enable. And the clock name is smooth clock, high frequency, low energy, and true. This clock turns on the low energy part of the CPU so that we can use it, because by default it's switched off to save power. Then we also need to turn on either low frequency external oscillator or low frequency RC oscillator. This one is built in. The second one is external. So if you haven't soldered it to your board, when you create a board, you cannot use it because it's not there. On these development kits, the crystal is soldered onto the board, but initially we will not use it. We will use low frequency RCO. So we need to turn it on. So we need to write CMU oscillator enable, where we turn on a certain oscillator, and its name is small ost. Oops. Low frequency RCO and true. And the second argument is should the code wait for the oscillator to start up, true. So it turns it on and then it waits some microseconds for the oscillator to start oscillating. It's hit by electricity, it's given a pulse, some voltage, and then it starts to oscillate, but it takes some time for it to reach full amplitude and frequency. So the CPU automatically waits for it to happen. And the second thing is low frequency RCO goes in here, and real-time counter is clocked from low frequency A clock. So this is like another separate low energy domain, and we need to turn this thing on, and then low frequency real-time counter, because there's also this low frequency B block, which contains low energy UART0 and low energy UART1. Oftentimes we want to run low energy UART at high energy maximum speed. So this domain can also be clocked from the CPU to get higher frequency. So this is why it is on a separate branch. However, these low frequency real-time clock, low energy sense, low energy timer, they're usually only clocked from low frequency RCO, so they have like a separate domain. This is why they are separate: low frequency A, low frequency B. So we need to turn low frequency A domain, and we do it with clock management unit, clock select, set, clock select set. Basically, we're with this function, we're manipulating this switch, and we select which clock source we want, either high frequency core clock, or low frequency external oscillator, or low frequency internal oscillator, or this ultra low frequency RCO. This one is 1 kilohertz, but it is extremely imprecise. This is more precise, and this is maximum precision. So we want small clock low frequency A to be clocked from small select low frequency RCO. This code is also in code examples which are offered by Silicon Labs. So even if I didn't show you what to write here, you could create an example project and just look at the code there and just copy the code from there. So you don't have to be born with this knowledge, but you obtain it by just programming this thing and taking examples from Silicon Labs. So this code is also from an example project. So this is how I know it, and you can just type it down and learn. So now we have turned on the clock for registers, the clock for low frequency RCO. We have selected that we want this LFA branch to run from low frequency RCO. And now we can start initializing our real-time clock. So the first thing that we need to write is we need to select prescaler, and then we need to enable this clock with this prescaler. So it's again 2 lines, but they're from clock management unit underscore. So first the signal comes here and goes to prescaler, and to save energy, we want to run this low frequency clock from as low frequency as possible. And if we want to have just 1 tick per second, then we can divide it down to, for example, 2 ticks per second, and it counts to from 0 to 1. And then on overflow, it overflows back to 0. So basically, half a second it counts to from 0 to 1, another half a second from 1 to back to 0. So we will just use maximum divider so that we save energy. So clock management unit, clock division set, and we want to manipulate small clock underscore RTC, and we want divider to be the maximum possible. So small clock division, and the largest that we can select for a real-time clock is only 1638, 384. It's mentioned somewhere in this data sheet. Yeah, it basically is mentioned here. The prescaler can be up to 2 to the power of 15, which is 16384. Okay, so the next thing is that we want to turn this real-time counter on. And this we can do by enabling its clock. And we simply write just as before, smooth slots enable. Smooth slots RTC. Oops, too many brackets here. True. So just like we enabled UART and timer and GPIO, we also enable real-time clock, except that we had to turn on low energy part, select the clock source, enable oscillator, and select the prescaler. So this thing manages the clocks. Next thing that we want to do is we want to initialize our real-time counter. And the real-time counter is really, really simple and basic. If it was complicated, it would consume a lot of energy. And basically, this counter simply has a counter and compare register comp 0. And also compare 1. And the compare 0, in this case, can be set as the top value of counter. So the maximum prescaler is so the frequency of low frequency RCO is 32,768 divided by 16,384. So we get 2 ticks per second. And if we set its top value equal to 1, then it counts 0, 1, it's easily overflown, and so it resets to 0. So we want to set its ceiling value to 1, because it counts up to and including a certain value. And so we need to write into compare register 0, value 1, and it's pretty straightforward. We can use real-time clock libraries function called Rtc compare set. And then we select which channel, compare channel 0, and the value up to which it should count, which is 1. Make Rtc overflow once per second. Then we need to make this initialization structure, Rtc init type def, my Rtc settings equals to curly braces open and closed. I control click on this thing. Here's the Rtc init defaults. I copy these defaults and I paste them here, and then I check out what these settings do. I don't like that I had to have a separate function to set the top. It should have been put into the settings structure, but Silicon Labs programmers decided not to make it this way. This is why this Rtc settings don't hold the top value. It's unfortunate, but fine. So in my Rtc settings, we just have 3 properties. Either the clock should be turned on or off, or enabled or disabled. Should it run during debug halt, or should it be paused? Usually we want to pause it so that when we press pause on our debugger, then all the CPU is paused, including these low energy clocks, instead of them running and doing something. And should the counter count all 24 bits, or should it stop at comparator number 0 value? We want this to be true, so that it counts from 0 up to comp 0 value, which we set to 1 here. So it should be set true that we want it to start running, false that it should stop during debug halt, and it should be set true that this thing restarts counting from 0 when it reaches comparator 0 value. So basically that's it. I just write Rtc init and I give address of my RTC settings. In this case, and in many cases, usually the microcontroller only has one real-time clock, so there is not RTC 0 or RTC 1. However, newer processors start to have them. So there is a group of newer processors where you also need to tell which counter you want to initialize. But for these older processors, there's only one real-time counter, so just real-time counter init, my address of, so ampersand sign here, which is shift +7, and then my real-time counter settings. And after this, the real-time counter has started to run. And then what we want to do is, for example, to check out that it really works, we want to enable real-time counter interrupts so that on every overflow, which is once per second, it calls an interrupt and, for example, turns on the LED number 1. Okay, so let's write this code. First of all, we need to enable real-time counter uh, overflow interrupt locally. So RTC int enable. And now, what is the name of real-time clock flag for overflow? I don't know, but if I start writing RTC EN, which is interrupt enable register, and press Control space, it offers me all of these values. Here's basically 3 possible values for overflow. Either it happens when real-time counter is equal to comparator number 0, or when it's equal to comparator number 1, or on overflow. But overflow happens when real-time counter counts to its maximum value of 22 to the power of 24. Since we set its ceiling equal to 1, then the only thing that we can use is when it matches the comparator number 0, it calls the interrupt. So it will be once per second. Then we also have to enable real-time clock interrupts globally. So I type nested vector interrupt controller underscore enable IRQ, and as an argument is RTC underscore IRQN, like this. So because it has 2 levels of switches, so locally and I enable which thing will cause the real-time counter interrupt, and then I enable real-time counter interrupts globally. And this thing is initialized, the clock will start running, and after every 1 second, it will automatically call the interrupt function, which now we need to write. So interrupt functions have just one format, which is void RTC underscore IRQ handler void. So the format of all IRQs in these processors is peripheral name underscore IRQ handler. So if I control click on this, I can also go to the list of all valid interrupts. The only thing that we can see is that UART0, for example, has 2 separate interrupts, one for receiving bytes and another for transmitting bytes. Other peripherals only have 1 interrupt. For example, analog to digital converter only has 1 interrupt. Because usually for sending and receiving, we want them to run separately. So like this. So in the interrupt, what we need to do is we need to clear the flags. So I type unsigned integer 32-bit flags equal to real-time counter int get. This real-time counter int get just returns interrupt flags. And the second thing is we want to clear these flags with RTC int clear flags. And again, int clear simply writes the flags into interrupt flag clear register. So we could have also written simply RTC interrupt flag clear equals to RTC interrupt flag register IF. This one line basically does the same thing that these two lines do. It's just that people like these beautiful names of these functions, so it's much better readable what exactly this thing does. And a good compiler will actually optimize this code in such a way that it sees, oh, you're reading some register into flag and then writing the value into another register. Why not skip the flag and just copy from this to this immediately? Good compilers will actually optimize the code, so you don't have to really worry that much about that. Okay. So, and what we want to do in this interrupt service routine is just toggle the LED. So we can use the LED function, but we will modify it. We will add a new function, void LED toggle, which means to switch the LED to the opposite level, and then LED numbers T LED number in this leds.h file. Then I go to leds.c file, and then I add this new function, curly braces open and close, and then again, if LED number is equal to LED 0, then, so how can we change the brightness? So if we want to toggle the LED to the opposite level, we need to read its current brightness. If it's greater than 0, then we set it to 0. And if it's equal to 0, then we set it to 100%. So here, to toggle this pulse width modulated LED, we need to write this code in the following way. If LED number is LED 0, then 32-bit integer current brightness equals 2, and maybe we actually used it. We need to read the current brightness, which is located in timer 3, capture compare channel, sorry, with capital letters, capture and compare channel number 2, variable called CCV. Then if current brightness is greater than 0, it means the LED is on, and we need to set it to 0. So I can use this LED 0 set brightness to 0. Else, if it's equal to 0, then we need to set it to 100%. This is for LED 0 because it's pulse width modulated. However, for LED if LED is LED 1, then we just need to set the port E pin 3 to the opposite level, and it can be done using GPIO pin out toggle function. So we have pin out set, pin out clear, but these ARM processors support pin out toggle. It's built in, which just sets the pin to the opposite level. So I can write here GPIO pin out toggle. It is built-in function. Port is LED1 port and pin is LED1 pin. And this toggles it to the opposite direction. So this is how I had to update this LEDs.h. I added one line, void LED toggle, LED number, T LED number in LEDs.h file, and in LEDs.c file, I added void LED toggle, LED number. I read if it's LED number 0, which uses timer 3 pulse width modulation. If current brightness greater than 0, then we set it to 0, else we set it to 100%. And if LED number is LED 1, then we just toggle the pin level with this built-in toggle functionality of GPIO peripheral. Okay, now to use the LED toggle function, I also need to include it in systime.h. So in systime.h, I write hashtag include and double quotes LEDs.h, so that this C file has access to library that LEDs.h and this LED toggle function. So, and in systime.c, in real-time counter ERQ handler, we just write LED toggle, LED toggle, and LED number is LED1. So once per second, this thing turns the LED on, and after 1 second, it turns it off, and then it turns on, and then it turns it off, and so on. So now let's test out our library. So this is systime.c, this is systime.h, this is the end part of LEDs.c, this is LEDs.h, and in main code, basically what we can do is we can do the following thing. I will delete this part. I will read print hello world. And, you know, for testing purposes, this thing will not do anything more. Just type hello world and delay 1 second. And we'll just check out if the LED is actually toggling. So I build this thing. There's no mistakes, apparently. Size is 19.7 kilobytes. And then I flash it into the development kit. Close. And now let's look at the termite. I clear it, and it looks like it's sending hello world every second. On the development kit, the LED is on, it's not blinking. So we need to check out, maybe there's some kind of mistake. So to debug this code, I don't know what the problem is. LED1, pin out toggle, LED1 port, LED1 pin. I don't know what the problem is, but what I'm going to do is I'm going to use a debugger to check out if we ever reach this interrupt service routine. So in this code, systime.c, I double click on, for example, the entry point of real-time counter ERQ handler, and then I press debug button. And what this does is it compiles the code, it flashes the code into the processor, and I can run it, and I can wait and check out if the code ever reaches the interrupt service routine, and it doesn't. You see, it never goes, so probably this real-time counter hasn't been started. And now I remember that in the main code, we need to actually call this systime init, otherwise there's no code that calls this systime init and starts our timer. So in main code, we obviously need to add one more line, which is called systime init. And we build it, and we get a warning that system init is implicit declaration. So in our main code, we also need to add hashtag include system.h like this. And now I build it again, and this warning will disappear. And it takes 21 kilobytes. Okay, so previously, when no code called the system function, then this system function was probably, just removed from the code because nobody ever calls this function. So it just removed to save the space in flash memory. But now I added it, and now it's being called, so it should work. I compile, I flash to device. Oops. And now the LED is blinking. Okay, now let's try to use energy modes. If you should go to launcher and look at compatible tools, and you can click on the EFM32 starter kit, and then under compatible tools, an energy profiler should appear. Click on the energy profiler, and this is the cool thing about this development kit, is that it's capable of measuring the current consumption of your device. So let's check out. Click quick access, start energy capture, select the development kit, click OK, and this thing starts sampling the current. And as you can see, the current consumption is looking like this. So I'll put a pause, and I will select some part, and I will zoom in. And as you can see, when the LED is off, we have a little bit lower current consumption, which is 4.78 milliamps, sorry, 4.54 milliamps. Here you can see the selected portions power consumption. And when LED is on, it's 5.04. So from this, we can actually calculate the current through LED. So it's 5.04 minus 4.55 is 0.49 milliamps. So the LED is consuming approximately 0.5 milliamps, not very much. However, generally, this processor is in active state all the time because it's actively making this delay 1 second function. So I click end session, and now we need to improve the code in such a way that it saves some energy. So for example, it types hello world, and then it goes to sleep, and instead of actively waiting for 1 second. So I click on Simplicity IDE view. And first of all, let's destroy this delay 1 second function. Well, okay, maybe I leave it here, but I just delete it from the main code. And instead of calling that, we will make a very common trick, which is called this. We will put the microcontroller to sleep after writing hello world, and it will just be in sleep mode. Its clock will be switched off so that it saves power, but the real-time clock is running from a separate clock source. So it will keep working, and after 1 second, when the interrupt routine happens, interrupt routine automatically wakes the CPU up and goes into main code, and the program continues working. So it wakes up, it does the interrupt service routine, and then it goes back to main code, and the main code resumes. And it will print out hello world again, and then again go to sleep. How can we put a microcontroller to sleep? We type energy management unit underscore enter EM2. And it has one argument, whether to restore clocks or not. In our case, we will type false, so it works faster because we're not using external high frequency clock. But to use energy management unit library, we also need to include it in mlib. So in mlib folder, right click, browse files here, and select MU, energy management unit, drag and drop into mlib library, Studio SDK location. Okay, here it is. You also need to include hashtag include it in mo.h in your project. And now what this thing does is it types hello world and goes to sleep by stopping the CPU. It just stops and turns off high frequency clock and nothing happens. But in the background, the real-time clock is running from a different clock. And when this 1 second passes, it wakes the CPU up to execute the ERQ handler, this interrupt. And after interrupt, the CPU stays on, so it resumes the action and goes into this loop back and types hello world again and goes to sleep again. So this is how it works. Let's compile. Sorry, something wrong. Okay, to use this EMU, we also need to include those files here, core, emcore.c. Let's try to build it now. Okay, so now I build it because EMU relies on core, so I had to include it as well. So now it works. So I compiled it, 22.4 kilobytes. Now I will flash it into the development kit. Okay, and the text is being written. And let's go to Energy Profiler, start energy capture, and let's check out what the power consumption will be now. And as you can see, the power consumption is a lot smaller. So I'll put pause. Let's zoom in and check it out. So when the CPU is sleeping in energy mode 2 and the LED is off, it only consumes 1.52 microamps. So it's 1,000 times less than when it is active. Then after 1 second, it wakes up. So you have this small spike. In this spike, you can, zoom it in. During this spike, it first executes the interrupt service routine. Maybe it takes, I don't know, a few microseconds. Then it sends the hello world message, hello world, and then it goes to sleep, but the LED stays on. And as you can see, practically all of the power consumption in this higher current consumption period is just LED current, 0.49, just as we calculated in calculator. Then it wakes up after 1 second, it performs the interrupt, then it sends out the hello world message, and then it goes back to sleep, and it goes back to sleep with LED off, so only the CPU backup real-time clock is on, and the current consumption is very, very small. As you can see, it's just 1.55 microamps, and so on. So here we see how we can take advantage of low energy modes. And as you can see, LEDs, even though this says LEDs are low current devices, for battery powered operation, LED actually is a big consumer of power. So normally when you create battery powered devices, when the device goes to sleep, usually the LEDs are switched off so that they don't consume power. And now also what we can do here is we can measure the precision of our oscillator. Let's check it out. Let's zoom in. And what is the time between the processor wake ups? It should be 500, it should be 1 second, but if I select from one peak to another peak, it says 1.06 seconds. Let's go to datasheet of this CPU and you will see something. So datasheet of the processor. Let's go to electrical characteristics of real-time of oscillators, and external low frequency oscillator properties are here, but we're interested in low frequency RCO. And as you can see, it's, it's approximately 32.768 kilohertz, but it's not actually very precise. It's at 3 volts and 25 degrees Celsius. It can be from 31.28 to 34.28 kilohertz. So it is not really that precise. External oscillators are something like, maybe 20 ppm, but this guy is a lot less precise. And as you can see, its frequency depends on voltage. So if you have low voltage, its frequency is actually really high, and at higher voltage it's lower. And at temperature, if you put it in cold place in a freezer, for example, its frequency goes down, and if you heat it up, the frequency goes up, right? So you can see it in this energy profiler. With energy profiler, this is another cool thing. If you make it in such a way that it switches something powerful on or off, you can also measure time with this energy profiler. And here you can see that, it's approximately 1 second, but it's not precisely 1 second. It's 1.06 seconds. And in many cases you don't care, but if you wanted to make a wristwatch with this thing, after 1 year it would be 1 month off. The offset is actually pretty big, maybe a little bit less than 1 month, but it would be actually several weeks off, because it's 6% imprecise. 365 days times 0.06, so it's 6%, is 21 days. So if you were running a wall clock with this internal RC oscillator, you would be 21.9 days off in your time. It would show 21 days ago in just 1 year. So if you need to just blink the LED approximately once per second, you can totally use it. But if you need clock capability, then you need to turn on and use external low frequency external oscillator, because they are much, much more precise. Okay, so let's go back to the code. First of all, you can just write down the code now and check out if it works, and check out that you can open energy profiler and you can, see that things are working this way. So this is the main.c file. In our project in mlib, we added core, energy management unit, and Rtc libraries. I also created systime C and systime H. In LEDs, I added LED toggle. In LEDs.c, I added LED toggle function as well. In systime H, I created this systime init, which starts a timer, which makes interrupt every 1 second. And in systime C, here's the initialization code for real-time counter, and the interrupt, which toggles the LED once per second. So you can write down this code, and you can compile it, upload it, and check out if it works. And you can see if it works or not. And your task is actually, there's a small task for you, which you need to add to your report for this lab, is you need to take your development kit and put it in some cold place. If you have a refrigerator, put it in the fridge, wait for a couple of hours for it to cool down, and then attach it to your, take it out of the fridge, attach it to your computer, and quickly open Energy Profiler and check out if the frequency is really lower, if the period is longer at low temperature. And then try to heat it up somehow. I don't know, maybe put it next to your computer's fan, or maybe um, use some heat source to heat this development kit up a little bit, only by a couple of degrees. Don't burn it, don't put it over a flame. I don't know, maybe boil some water and put it over the cup or something like that without the humidity getting to it. Just heat it up a little bit by some 10 degrees and check out if the period gets smaller. And then add it to your report for this lab so that I can see that you did this experiment, and maybe you can write some thoughts or just realizations about this real-time clock source called low frequency RCO. So that's your task number one. Write it down. Try to put the development kit in cold and in warm location. Maybe you can leave it in a direct sunlight, for example, so it heats up by some degrees. Or in my case, my laptop gives out pretty hot air, so I just put it next to the laptop so that this thing heats up, and measure the time. And the second thing that we will do it now. I'll show it to you, and you will have to do it like a second part of your report. Let's, instead of using internal oscillator, let's use the external oscillator. This development kit, as you can see in user's guide, this development kit actually has a soldered external low frequency oscillator. Let's see, is it somewhere here? I think this piece. On newer development kits and on older development kits, there's also this part is an external low frequency oscillator, and those are much more precise devices. So if you have, some extra money, you should put it. It costs something like 30 cents, maybe even cheaper. And if you add it to your processor, you get a more precise result. So in our development kits, it's soldered on. So let's turn it on. Let's use it instead of imprecise low frequency RCO oscillator. Let's check out how much better it is. So to use external low frequency external oscillator, basically you copy these two lines, then comment these two lines out, so that you have some reference. And here on oscillator enable, instead of low frequency RCO, delete, control space, and select low frequency external oscillator, true and true. And on clock select set for LFA, instead of low frequency RCO, use low frequency XO. So the API is made in this nice way that you just change a couple letters and you change the clock source. So oscillator enable low frequency external oscillator, and clock select set low frequency external oscillator. And that's it. With this code, I can compile it. It builds. It's approximately the same size. I will flash it into the development kit. It's working. And now let's go to Energy Profiler and start energy capture. And let's see if external clock is more precise, less precise, or maybe totally the same. Okay, so let's zoom in. Let's pause. Let's zoom in. And as you can see, now I have selected pretty precisely between the two peaks. And time is exactly 1.00 seconds. Okay, so in my case, I don't know, maybe you will get different results, but in my case, external oscillator is much, much more precise with this, energy profiler. My measurement shows that it's exactly 1 second period. With internal, less precise, more temperature and voltage dependent RC oscillator, it was 1.06 seconds, so it's a 6% mistake. But with external high precision oscillator, it's 1.00 seconds, so it's practically perfect. So in my case, external oscillator was more precise. And the second part of your practical lab work is you you do as I did by selecting a low frequency external oscillator and repeat the experiment once more, put the development kit in freezer, and then after an hour, attach it quickly to your computer and measure the time. And then put it in sunlight or next to your computer's fan, or try to warm it up in a different way and check out the frequency. Then just don't break it. Don't put liquids on this thing. Just be careful. I don't know. Laptop fan is probably the best thing. And then, compare the results. Is low frequency external oscillator better or not? And basically what I want you to do is you will, in your um, report, you add your code, and you also add, one page with Word document where you put the numbers that you got from external and internal oscillator, and, compare them with a couple of sentences. Okay. So that's all for today. I will again show the code. So this is systime.c with external oscillator switched on. This is systime.h. This is leds.c bottom part. The top part is the same. This is leds.h. And this is main code. Okay, so good luck.